For this lesson, we have interpretations and applications of the derivative and the definite integral. So how can we apply and interpret the derivative? How can we apply and interpret the definite integral? So we've definitely done applications and interpretations of the derivative before. We've taken a look at the derivative with respect to x or with respect to t of some amount, and that equals the rate at which the amount is changing. This is like our related rate stuff. So if the amount is like the height of a building, the ddt usually was how fast is the height of the building changing. If it was positive, then the height is increasing. If it's negative, the height is decreasing. There you go. For example, if water is being drained from a swimming pool and R of t represents the amount of water measured in cubic feet that is in a swimming pool at any given time, measured in hours, then R prime of t would represent the rate at which the amount of water is changing. So if you take the derivative of R of t, you get R prime of t, and that would have units of whatever the units of R are, which was cubic feet. So I'm going to put feet cubed per whatever the bottom label would be. So the derivative, I think this should really be a t. Derivative with respect to t, so the bottom would be hours. Okay, so the rate would be cubic feet per hour. Okay, the integral of a rate would then be the amount of change. So this is super duper similar to what we did with like net distance in the previous section. So the integral of the rate with respect to t, like a dt or something at the end, would equal the amount of change. How much did we start with? How much did we end with? So I've got a bunch of words here. In the context of the example situation above, what does this value represent? The integral of the derivative is going to equal the original function, right? Derivative, or the integral gets rid of the derivative sign, so there's no more little prime up here. And then plugging in b and plugging in a, we find the difference between the starting value and the ending value. So R of b represents the amount of water in the pool at t equals b, because R, we are told, is the amount of water in the pool at that time. R of a would be the amount of water in the pool at time a. That means that R of b minus R of a represents the change in the amount of water. Since that would be probably it's being drained. So we would expect there to be less water for R of b than there is for R of a. So R of b minus R of a represents it represents the amount. Oh my gosh, these are amounts. So you subtract them and you get amounts. The amount of water that has drained from the pool now that is just over this time frame, so from t equals a to t equals b. Let's keep going. The table below represents the velocity of a particle at given values of t, where t is measured in minutes. So we're given a velocity and time. That's it. We want to approximate the value of the integral from 0 to 30 of v of t dt using a midpoint Riemann sum, and then explain what does that mean. What is our answer? To find a Riemann sum, and we are using a Riemann midpoint sum. We're going to, we have to decide for ourselves how many intervals we're going to have. So going from 0 all the way to 30, we could do this in 2. We could go from 0 to 15, but then there's no midpoint, right? Between 0 and 15, midpoint would be 7.5. What if we go from 0 to 10? So that's going to be our first rectangle. From 10 to 20 is our second, and then from 20 to 30. That one's gonna work because we have midpoints of 5, 15, and 25. The widths of all of those rectangles are 10. The heights of the rectangles, use the height from 5, 1.6. Use the height from 15, 3.1. And use the height from 25, 1.6. So you add those guys all up, multiply by 10, and you get 63. And now we need a label. Okay, we are multiplying for our rectangles. We are multiplying minutes times feet per minute, trying to find an area. Feet per minutes times minutes, the minutes cancel out. Our area is in feet. Now, I know that that doesn't make sense like two-dimensionally. Area is usually like feet squared or whatever, but this is not an actual, how to word this? We're finding the area on a graph which represents a distance in feet. Okay. Or like the position in feet, right? So this 63 is feet. Okay. We could write this integral using the fundamental theorem of calculus. We could write from 0 to 30 of v of t dt. That's like p of 30 minus p of 0, which is the total change in distance. It's the net change in distance. Net distance, net change in distance, something like that. How far is it from the beginning point to the ending point? That's what that means. It's not in absolute values, so generally you wouldn't say that this is a total distance. However, since all those velocities are positive from the beginning to the end, right? They're all positive. It is probably also the total distance. And it goes from 0 to 30 minutes, since t was measured in minutes. Next one, we want the integral from 5 to 25 of a of t. Okay, that a of t is the derivative of v of t, right? So if this thing right here is the same thing as v prime of t, the integral gets rid of the derivative symbol. I'll scoot that up. The integral gets rid of that derivative symbol, and we're just left with v. Now, since we have numbers 5 and 25, this will be v of 25 minus v of 5, top one minus bottom one. And we know what 25 and 5 are from the table. They are 1.6 and 1.6. Subtracting those out, you get 0. Velocities, we're just subtracting velocities. So those are in feet per minute. Okay. A of t represents the change in velocity. The change in velocity from t equals 5 to t equals 25 minutes, right? We're subtracting velocities. That's a change in velocity. Done. We've got a word problem. I've got some stuff written down for this word problem as well. Let's go ahead and go through it. We are starting with the temperature of water in the tub, and it is strictly increasing. That means that it is never decreasing, and it is twice differentiable, which means you can take a derivative and then take a second derivative. Cool. W of t, which is the water temperature, is measured in degrees Fahrenheit, and t is measured in minutes. So we've got a table with some values. There's, of course, values in between. We know that our function is differentiable, so we know that this is continuous. This function, w of t, is continuous. Using the data in the table, estimate the value of w prime of 12. So we are estimating the slope of w at t equals 12. 12 is not on this chart, but 12 is between 9 and 15. So w prime is the slope of w So we are doing W of something minus W of something over, and then the T values down here. We are estimating using T equals 15 and T equals 9 because they are the two numbers that surround 12. So I'm going to toss a 15 and a 9 up there on the top. Okay, the bottom is 6. W of 15 is 67.9 and W of 9 is 61.8. And that equals 1.017, and we need a label. The label of the top, the label of W, is degrees Fahrenheit. The label of the bottom, which was time, is minutes. Okay, so this right here is a rate. This is the rate of change of W. Totally didn't even have that on there. The rate of change of W is about 1.017 degrees Fahrenheit per minute. Since it's positive, that means that your temperature is increasing. So let's write a sentence. At T equals 12 minutes, the temperature of the water is increasing. Oh, I forgot the word increasing. At a rate of 1.017 degrees Fahrenheit per minute. Cool. Next, use the data in the table to evaluate the integral from 0 to 20 of W prime of T dt. Using correct units, interpret the meaning of this integral in the context of the problem. All this interpretation. Okay, so W prime, we're taking an integral, so we're left with W. Integral gets rid of a prime. So this is W of something minus W of something. Fundamental theorem of calculus. 20 is going to go on the first one. 0 goes in the second one. W of 20 is 71.0. W of 0 is 55.0. And we subtract and get 16. W is measured in degrees Fahrenheit. There's nothing to divide, so we are done. Okay, we are subtracting W's. We're subtracting temperatures. That means that this whole thing represents the change in temperature. Or the amount that the temperature rose or something from T equals 0 to T equals 20. Okay, W represents the amount, so you could say the amount that the temperature rises. Last one, for T is between 20 and 25, the function W that models the water temperature has a first derivative given by the function W prime of T equals, and then that whole mess. Based on this model, what is the temperature of the water at time T equals 25? Okay, we want W, the water temperature, at T equals 25. This function is only usable between 20 and 25. We're looking for W of 25. Is what? We don't know. We know W prime. How do we get from W prime to W? Well, we take an integral, right? Integral of W prime of T dt equals, okay, we need numbers. We need a 25 in there. But when we do this, we need fundamental theorem of calculus. We need 2 times. So here's a 25, and then the only other valid number is 20. 20 also happens to be on our chart up here. So I'm going to refer back to that number here in a second. 25 is bigger than 20, so I'm going to put 25 on the top and 20 on the bottom. And this is going to equal W of 25 minus W of 20. Okay, we do not know W of 25, so that goes here. Minus W of 20 is 71.0. Now this guy over here, that's gross. What do we do with it? Well, we have a function. We as human beings cannot calculate this integral, but our calculator can. Our calculator, if you plug this into the Math 9 bit and use T equals 20 and T equals 25, you get 2.043. We used a calculator. math 9 to get that. And then your last job is to solve for W of 25, and we can add 71 to both sides to make that happen. So this will be 73.043 equals W of 25. We need a label. W is measured in degrees Fahrenheit, and that is our answer. At T equals 25, the temperature of the water is 73-ish degrees.